Right, so tomorrow we have to discuss about the tutorial 1. So today we just focus on the chapter 2. Okay, and then tomorrow we do the tutorial for chapter 1. So tomorrow we do the tutorial. So please make sure before we do the tutorial, you try first. Okay, and then we discuss tomorrow for your tutorial 1. Right, wait. All right, okay. So chapter 2 is the DC meter. So DC meter, direct, as I mentioned to you, is the direct meter. It's the direct current meter. So on the DC meter, we have the voltmeter, we have the ammeter. Okay, actually for ammeter is to measure the current. Okay, for voltmeter to measure the voltage lah. Right. So at the end of this topic, okay, so you should be able to sketch the construction of permanent magnet moving coil. Alright, or sometimes we call it the ensemble instruments, and then explain its operation. And then second LO is to design DC ammeter and design DC voltmeter using the ensemble instrument that I mentioned to you. So DC ammeter is to measure the current, and DC voltmeter to measure the voltage. Okay? So so for the third LO for this objective is the design multi-range DC ammeter and DC voltmeter using the Ariton shunt, and then define the load error and emitter excitation effects, and then last but not least is to design ohmmeter using the ensemble instrument. Actually, sometimes some of the book refer to the permanent magnet moving coil, or some of the book refer to the ensemble, but the both will be similar. It's the same. Okay, depends on the books. Sometimes they refer to the permanent magnet moving coil. All right, so this one. Okay, sometimes they refer to permanent moving coil, or sometimes they use the ensemble instrument. Right. Okay, so for the introduction for the DC meter is the basic meter movement used in DC measurement. Okay, it can be traced to Hans Oersted discovery in 1820 of the relationship between the current and magnetism. Okay, I'm not sure, maybe you remember the Fleming Fleming rules. Okay, we have the thumb rules. Do you remember the Fleming's Fleming hand rules? Okay, they have the right. Okay, they have right, left Fleming rule, and they have right Fleming rules. So I'm not sure. So maybe on the physics you are studying about this one. Okay, for example, for hand. Okay, can see my fingers. Okay, for the hand left Fleming rules for left. So actually this is our current. Okay, for the middle finger is our our current flow, and this one will be our magnetic field. All right, the magnetic field flow, and this one is our force our force. Okay, so actually for left is for motor, and for right is our generator. Okay, our generator, but the same the middle is our current flow. Okay, the middle is our current flow, the middle fingers, and the index finger will be on the magnetic fields, and the thumb will be our force our force, direction of force. Okay, or sometimes we can refer as the similar like this one, the thumb rules. The thumb rule, that means here the thumb will be our electric flow, and this one, the another finger will be our magnetic fields. Okay, our magnetic field. That means, okay, for example, current flow like this, from this one to this one, that means our magnetic field will be like this. Okay, follow the fingers, other fingers. All right, that is we call the thumb rule. Okay, for left is we refer to the motor, and then for the right we refer to the generator. Okay, remember before this, for the I'm not sure, maybe on the physics, so you are studying about the left Fleming's. Okay, flaming rolls and right flaming roll, right? For the left that I mentioned to you is the for motor, okay, for the motor, electric motor. And then for right will be for DC generator. Okay, so that is the basic concept of the relationship between the current and magnetism lah. For example, if you want to see the magnetic fields, okay, based on the current flow lah. For example, current flow like here to here. So the magnetic field will be follow the fingers lah. Should be like this. Okay, that's we call the thumb rules. Alright, so the JQs, the DR solver is patented the moving coil galvanometer lah. That means the DR solver instrument is based on the founder is the Jacob DR solver. Patented the moving coil generator. So actually the same basic construction developed by DR solver lah is used to meter movement today. So the permanent magnet moving coil (PMMC) instrument meter movement refers to as the DR solver meter movement lah, that mentioned to you. Some of the book they are refer to the DR solver, okay, meter movement, or some of the book they are refer to the permanent magnet moving coil. That is the same same things lah. Actually, is the both will be similar, alright? But it refer to the books lah. If some book refer to the DR solver, or some of the book refer to the permanent magnet moving coil, PMMC. Okay, so you can see on the figure 2.1 is the PMMC instrument. Alright, actually this is analog. Okay, the analog. Okay, this is analog, DC analog in analog. Normally nowadays we use the digital lah. I mentioned to you before this, to measure the voltage, to measure the current, we just use the digitals. Okay, but actually we have to know the analog. No analog, no digital. That's why you have to learn. Okay, the analogs. Okay, the analog lah. Okay, the digital come from analog lah. Okay, this is digital instrument lah. That means to measure the current, to measure the voltage, we just use the digital multimeter. Alright. For example, yeah, this one you see this DC meter or this DC meter for ammeter and for voltmeter they use the analog. This one is the analog lah. You can see, alright, the figure 2.1 show the horseshoe shaped permanent magnet with the soft pole, okay, soft iron pole here. Alright, so okay, between the north and south is the cylindrical lah. Okay, this north and south they have the cylindricals, okay, shaped soft iron core. Okay, this one and then we have the winding here lah. Inside this one we have the winding. Alright, with coil iron of the fine wire is wound here around this one. Okay, this is fine wire is very light metal frame and mounted in the dual setting so that it can rotate freely lah. This one this is pointer. Actually this pointer depends on the current lah, on the current. So for example, this is low current and moving to the right will be high current lah, for example. So actually this pointer will be depends on the current flow on this winding. Okay, this winding lah. So if you have large current, that means our pointer will be to the, for example, to the right. Okay, that is its function for the solver movement meter. Alright, you can see this one. So the moving coil depend on the amount of current through its winding lah, that mentioned to you. So if we have large current, so our pointer will be reflects to the amount of current through the winding lah. Alright, that's why you can see this one. The pointer attached to the moving coil reflect up to the scale of the moving coil rotate lah. Okay. Alright, so we go for the DC ammeter that mentioned to you. DC ammeter is direct current ammeter, is to measure the current lah, to measure the current. So ammeter to measure the current and voltmeter to measure the voltage lah. Okay, so for DC ammeter, we've used the parallel connected resistor. It can be employed to measure the direct current levels. Okay, this is done by placing the low resistance with the parallels with the meter movement resistance Rm. Okay, and then this low resistor is called the shunt resistor. Low resistor is we call the shunt resistor, and its function to provide the alternative part for the total meter current I around the meter movement. So I will show the For example, this is you can see this one. All right. So this is the ensemble meter. Okay. You can see this one. So the RM will be parallel. This RM, okay, will be parallel with shunt resistor lah. Okay. So for example, to calculate the current here, actually, okay, so will be same with the current here. Okay. On theoretical, the current in series will be same. Okay. The current, for example, we have this example, we have resistor here. Okay. So this is our current. Right, so this is our current. Okay, this current, for example, current 1. All right, so this is also current 1. All right, so please remember this one. The current in the series will be same. Okay, the current in the series will be same, but the current in the parallel will be separate separate. For example, you can see this one. So here we have the branch. Okay, branch here. So once go for the here for shunt resistor, another one go for RM here. All right. So depends of amount of resistor. If the higher or the greater number of resistance, the lower current. Okay, the lower current. The concept of current will be flow to the lower resistor. Okay. For example, like if we put here, okay, we put some wire here to this point, so automatically this we call the short circuit. Okay, so the current will be flow from here to this one, this point. So we will avoid this, okay, to RS and RM. Okay, that is the concept of current. That means the current will be flow to the lower resistance. Okay, for example, so okay, for RS is lower. That means the current on the IS is the higher compared than RM. Alright, that is the concept of current. Okay. Clear, guys? So current, make sure you have to remember this one. Current in series, okay, will be same. Okay, you can see this one. Okay, this one. All right. So for example, we have this one R1, this one R2. All right. So current here will be same with current here. Okay, that is we call the current concept lah. Okay, the current in series will be same. Okay, current in series will be same. All right. But the current in the parallel will be different. Okay, compare then, for example, like voltage. Okay, voltage in parallel will be same. That's why you can see this one. Voltage here to this point actually is same with voltage for this point to this point. Okay. Right. So the voltage will be same. Okay, for example, we declare this one as the VM. Okay, this one we call as the VS. So automatically we know VMs equals to VS. All right. So that is the concept for the voltage. Okay, voltage in parallel will be same. Okay, but voltage in the series is not same lah. For example, this one. So this one will be different lah. This one V1 equal to I1 multiplied by R1. Okay, so this one for the voltage V2 equals to R2 multiplied by I1. All right, so that depends on the amount of resistor here. All right, so that's why the voltage, okay, the voltage in series is not same. All right, but the voltage in parallel will be same lah. Okay, you can see this one. The voltage parallel. Okay, this one. This point to this point. Okay, and this one will be same. That's why VM equals to VS. All right, but the current will be different. So here we have the IM through here, and another one we have the IS through here lah. So you can see IM is the full scale deflection current of the meter movement, and I total is the full scale deflection current for the ammeter lah. So this is our our ammeter to measure the amount of current flow to IM here, right? That mentioned to you, if you want to measure the current, okay, so for example, we use the digital multimeter here, all right? So we have to make sure, so we have to connect like this, okay? For example, this point, okay, this point, to this point. All right, then we can measure the voltage. We can measure the current. Okay, if we put like this, okay, okay, point here one, another one here, so automatically will be short circuit, will be short circuit. So maybe our digital meter will be broken. So, okay, depends on the fuse. Okay, for example, our current will be high, so that's why our digital multimeter will be broken lah. Fuse will be blow. All right. That's why we have to make sure if you want to measure the current, make sure connect in series, similar like this. This one, you can see this one. All right. So this one connect with series. All right. That's why we can measure the current here because there's connect in series. It's not connect in parallel. Okay. Cannot connect in parallel. If connect parallel, so that's mentioned to you, the concept of current will be flow to the lower resistor. Okay, lower resistor. For example, that I mentioned to you. So if we put here wire to this point, so this wire, so automatically this is short circuit. Okay, not current will be not flow to the RM or to RS. So the current will be flow here. All right, the current will be flow here. So this one current will be zero. Current will be zero. That's why we call the short circuit. All right. So you have to remember this is a basic of electrical. So the current, okay, the current flow in series will be same, okay, and then the voltage in parallel will be same. All right, that is the basic of the fundamental of electrical. For example, like this. So the voltage in parallel is same, and then the current in series will be same. Okay, that is concept of electrical. You have to remember this one. Okay, so that I mentioned to you, and then you have to calculate the voltage here. Okay, the voltage here. So I am here. So this one we call the IM. So this one IM multiplied by RM. IM here. So we got the voltage here lah. Okay, to get the voltage here. All right. So VS equals to IS RS. Okay, that is same concept. That means VS RS is the same voltage. Okay. Okay, you can see this one. So the mention to you because the voltage, okay, in parallel will be same. All right. So that's why to calculate this one, you use a formula lah. Okay, this formula come from derivation. So you can substitute this formula, and then at the end to calculate the shunt resistor here, use this formula lah. Okay, using this formula. IM, okay, divide by I total minus IM multiplied by RM. That is for calculate the the shunt resistor here. Okay, that is formula lah. So up to you. You want to remember the formula, up to you. But for me, better you have understand how to get this formula from the concept of electrical lah. Okay, that mentioned to you. So if current in series will be same, and then the voltage in parallel will be same. Okay, that is the concept, basic concept of electrical. Right. So this some example. You go for the example. So you can see this one. So if you use the formula, okay, this is formula. Calculate the RH equal to IM divide by I total minus IM multiplied by RM. Okay, you can straightforward using the formula lah. For example, okay, IM. Okay, where is the IM? IM is the given to here. IM is the 1 milliampere. Okay, 1 milliampere. All right, divide by, okay, the I total is this one, the maximum. The maximum is the 10 meter. 10 milliampere. Okay, 10 M minus I, okay, 1 milliampere multiplied by, okay, what RM is 100 lah. Okay, hundreds. Okay, so 1 over 9 multiplied by 100. Okay, so use your calculator. 1 over 9, okay, multiplied by 100. So the same answer lah. Okay, so the answer will be same. Okay, so that's why you can straightforward. Okay, use 11.11 volts ohm. All right. So you can straightforward using the formula, okay, to calculate the shunt resistor, or you can derive. This one you can derive. First, for this one, the solution, they calculate the VM. Okay, calculate the VM uses the formula. Okay, IM given, okay, multiplied by RM. RM also given hundreds. Okay, so they get 0.1 volts. Okay, 0.1 volt. That I mentioned to you, VM equals to V shunt. Okay, voltage shunt here. All right, so that's why voltage will be here. 0.1 will be same. And then for current shunt, current total, okay, actually current will be current total. I put current total will be IM plus I shine. Okay, that's why if you want to calculate the current I shine, so automatically I totals minus by IM. Okay, that is come this equation comes from this one lah. Okay. Alright, okay, so you get at the end, calculate the using the formula, Ohm formula, V equals to IR. Alright, to calculate the R equals to V over I. Okay, that's why you can get 0.1 divided by 9 milliampere. So the resistance, okay, shunt resistance is the 11.11 ohms. Okay, that is the how calculate. You can straightforward using the formula. All right, you can straightforward using the formula. This is formula to calculate the R shunt, or you can solve using this one. This one from derivation. All right, so the purpose of design the shunt circuit is to allow us to measure the current. Okay, that is some number of n times larger than IM. All right, the number n is called the multiplying factor and relates to total current and meter current as, okay, this is I total. I total equals to n multiplied by IM. Okay, this one. This is formula for multiplying factor lah. We call the multiplying factor, and then this formula we substitute to the okay, we substitute to the formula formula 2.1. Okay, formula calculate the R shine. So we get like this lah. Okay, and then simplify. So cancel out the IM, cancel out the IM. So we get this one lah. Okay, RM divide by n minus 1. So from this one, IM, okay, RM, IM, okay, n minus 1 lah. All right, so let's cancel out the IM. So will be like this lah. Okay, RM over n minus 1 lah. Okay, there is formula, another formula to calculate the shunt resistor, but we have to calculate the multiplying factor first. Okay, that is another technique lah. Okay, so next we go for the Ariton shunt. Okay, so on the multi-range ammeter, so the Ariton shunt or the universal shunt is more suitable design. Okay, so this one we want to measure more than one parameter. Okay, for example, we want to measure from 10 milliampere or 1 milliampere or 0.1 milliampere and so on. So, okay, that's why we have to use the Ariton shunt. Okay, the Ariton shunt is to apply more than one parameter. Okay, more than one range. Okay, for the measure the current. Okay, the advantage of Ariton shunt is to eliminate the possibility of current overload, okay, of the moving coil. For example, we know, so maybe we can set the range lah. For example, okay, this is for example like our digital. So digital also we can select the range. Okay, for example we can put the range lah. That's why we have to need we call the Ariton shunt lah. Okay. So they protect the deflection of instrument of the ammeter from the excessive current flow lah. Okay, so it may be used in the wide range of the meter movement. Okay, so this is, you can see the similar like the ensemble, but they put some. Okay, you can see this one. Okay, they have the parameter first is the 10 milliampere, second range is the 100 milliampere, and then third range is the 1 ampere. Okay, 1 ampere. But it's similar like the ensemble. The ensemble only one. Okay, so only one. We have the R shine here, but here R shine for the Areton will be RA plus RB plus RC lah, for example. Similar like before this, same. Okay, that mentioned to you. Okay, so they have three parts. For example, they have three parts. First, we have select to part A. Okay, part A. So how to select the part A? Okay, this is will be same lah like previous. But the R shine will be RA plus RB plus RC. Okay, that is for resistor here. Okay, if part B, we select the part B here. We select, okay, this selector, we select to this one. That means this RM will be series with RA and parallel with RC series with RB. That means RC plus RB. This one RM plus RA. Okay, that is for part B. If we select for the 100 milliampere. Okay, for part C, we select the 1 ampere here. So that means we select here. Okay, so that means RC parallel with RM plus RA plus RB. Okay, plus RB. That is another resistor. Okay, resistor dimension to here. Resistor in series will be plus. Okay, for example, R1, R2. So automatically R total will be R1 plus R2 lah. Okay, but in parallel, so if parallel, so some similar like this. This is connected in parallel, for example. Alright, so this one R1, R2. So the R total will be R total R1 plus R2. Okay, that is for parallel resistor. Okay, parallel resistor you have to call it measure like this. But in series just add. Okay, for example, resistor in series just add lah R1 plus R2. Okay, for example like this. This is part 1. Part 1 that I mentioned to you. Alright, here. So that means the RS, the shine resistor will be RA plus RB plus RC lah. That's why I got like this. Okay. And then you have to calculate the voltage resistor lah. Okay. Sorry, the shine resistor. Okay. Shine resistor you can use this formula lah. Okay, use this formula or this one. Okay, that is for part 1 lah. Part 1 Okay, if you can see the part B that I mentioned to you so the RC and RB will be plus and then parallel with RM. Okay, you can see this one that I mentioned to you, the part B here. We connect to the part B selection here. So that means this RA series with RM but parallel with RB and RC will be series. Okay, that's why on the part B you can see this one the voltage will be okay, the resistor RC plus RB and RM plus RA lah. Okay, this is parallel parallel voltage. That's why you can see the voltage will be same here. And then just substitute the formula. So this is the formula lah to calculate the RB and RC. So this is formula. Okay, this is the derivation. Derivation to get this formula lah. Okay. Alright, so we go for the part C. The part C that I mentioned to you, the RC. Okay, part C here. We connect to this one 1M. 1M here. So that means RC parallel with RM plus RA plus RB. Okay, that's why you can get like this. Okay, that's why RC. Okay, this is, you can see this one. This is voltage for RC. Sorry, VC. This one voltage for VM. VM. So this one we call voltage shine. Okay, but the resistor here will be plus. That's why you can see this one. The resistor RA plus RB plus RM. Okay, and then they simplified the formula. So this is formula to calculate the RC. Right, calculate the RC. Okay, that is how it derived lah. Okay, but you also can memorize the formula. Okay, this formula. Okay, this is calculate the RC, and from the RC, okay, you can get the RB. Okay, from the RC, and then after calculate the RB and RC, you can calculate the RA here. All right. Okay, so this is some example lah. Okay, class. I will stop here first because I forget to update my Zoom. So and then I will continue. I will pass the new link. Maybe I can use another I try use the Google Meet. Try use the Google Meet because less than 1 minute will be shut down. So this Zoom will be shut down because I forgot to update. Because if you want. All right, so let's continue. Let's continue our example. Okay, for array shine. So you can example 2.2, compute the value of shunt resistor of the circuit as shown in the figure 2.3 lah. This one, similar like this one, Okay. All right, so that's why you have to calculate the RA, RB, and RC lah. All right, so the part 1, okay. Okay, the part 1 you have to calculate the. Okay, this is part 1. For example, we connect to this one, this part. Okay, to this part. Okay, we connect to the 10 milliampere. 10 milliampere. That means R shine will be RA plus RB plus RC parallel with RM. Okay. Okay, this is part A lah. Part A. Okay, so this is, for example, I1 we know 1. Okay, I1 is the 10 milliampere. Okay, divide by IM is the 100 microampere. Okay, so the amplifying factor is the 100 lah. So 100, and then you have to calculate the resistor R shunt here. So using the formula, okay, formula. So this formula will be given lah. Normally RM over N minus 1 lah. So RM is 1K, okay, 1 kilo ohms, okay, divide by hundreds minus 1. So that's why our R shunt will be, okay, will be 10.1 lah. So if we know this one, R shunt will be 10.1 ohm. That's why we have to calculate the RA, what is the RA, what is the RB, and what is the RC. Okay, here. But the total for R shunt will be 10.1 ohms. And then this is normally part 1 you have to calculate the part 1 to get the R shunt total. Okay. And then you have to go the next step. We have part 2 lah, part B. Okay, part B you have to calculate the RC. Sorry. Okay, calculate the RC here. Okay, so this is formula lah, formula to calculate the RC. All right. So if you're not formula, if you not remember the formula, you can derive. Okay, that means you can derive lah from this one, from part B here. Actually, you can derive here. So actually, formula will be given, formula will be given. But if you not remember the formula, okay, just you can derive start from here lah. Okay, that means that I mentioned to you, if part B, okay, we connect to this one, connect to. That means here we connect to this one, okay, part B. That means RA and RM will be parallel, will be series, parallel with RB, series with RC. Okay.
Yeah.
Okay, this is for part B, for part B. Okay, substitute the formula. So at the end you got the, okay, the RB plus RC is 1.01 ohms. Okay, this is for RC plus RB. Okay, and then to calculate the RA, okay, using this formula R shine minus RB plus RC. Okay, so that's why you can get the RA. After you get the RA, you can get the RB and also RC lah. Okay, and then the part C, Okay, this part C, the formula for part C lah. Okay, and then you substitute the formula, substitute the value of for example like IM, okay, resistance shine and RM, so automatically we get the RC lah. So please make sure after you get RA, RB and RC, okay, you have to double check. Okay, that's mean okay. Sorry. Okay, okay. After you calculate the RA, RB and RC, make sure you calculate. Okay, make sure same. Okay, RA plus RB, okay, plus RC. Okay, make sure is the correct answer lah. Okay, if not, you have to double check. Okay, which one is not correct lah. So that's why after you calculate the RA, RB and RC, you just add RA, RB, RC, and then check with resistor shine resistor here. So it's same, that means your calculation is correct. If not same, so that's why you have to double check lah which one is not correct. Either you have to calculate again what is the shine resistor, or you have to calculate RA, RB or RC. Okay, the concept is shine is equals to RA plus RB plus RC lah. That's why if you say example like 0.1, okay, plus 0.9 plus okay, plus RA is the 9.09 lah. So that's why the total resistance, shine resistance is the 10.1 ohm. That is formula to calculate the return shine. Alright, so next, okay, next we go for the DC voltmeter. Okay, for DC voltmeter, we have to measure the voltage. Okay, we want to measure the voltage. Alright, so you can see to measure the voltage, we can use the ensemble instrument. Okay, as the DC voltmeter by connecting the multiplier RS in series with the meter movement as shown in the figure 2.4 here. Alright, so before this, for current, so we connect with parallel. But for the DC voltmeter, we connect with series lah. This one okay, the RM and then series with RS here. Okay, so this is we call the voltmeter lah, using the ensemble meter movement lah. Okay, so we can put here. Okay, right, so the purpose of the multiplier is to extend the voltage range, okay, of the meter and limit the current through the ensemble meter to the maximum full scale deflection lah. Okay, that I mentioned to you. So if we connect with series, so we have the voltage drop here. We have the voltage here and we have the voltage here. That's why the function of this one, the RS, to limit the current through. That's why with this resistor will be function of to limit the current through this, okay, meter to this meter, the ensemble meter. All right. So next, to find the value of multiplier resistor is required to determine the sensitivity lah, all right, of the meter movement. So the sensitivity is found by taking the reciprocal of the full scale deflection current as written as the right sensitivity. This is formula. You have to remember this one. This formula for sensitivity, 1 over full current. 1 over full current. Okay. The unit is the ohm per volt lah. Okay. The unit for sensitivity, the ohm per volts. Okay. And then from sensitivity, we can calculate the multiplier resistor lah. Okay, multiplier resistor. This formula for multiplier resistor. All right. So equals to S is the sensitivity. This one okay. This one is we call the sensitivity multiplied by range. Okay. Range. Okay. The range we normally we be given, and then minus with internal resistance. Okay. Or we can set this one R. Here is the R total lah. Okay, R total. Okay, R total. This one R total. And then minus with internal resistance, we call the RS lah. Okay, so let's go for the example. You can see this one, the example 2.3. Calculate the sensitivity of 200 microamp meter movement, which is to be used as the DC voltmeter. Okay, first you have to calculate the sensitivity. Okay, this is formula for sensitivity, 1 over full current lah, full scale. Okay, this one we call the full scale. The full scale is the 200 micro, 200 microampere, right? So the sensitivity is 1 over 200 microampere. So actually this is, okay, this is 1 volt, okay. And then, so the answer is the 5 kilo ohm per volt lah, 5 kilo ohm per volt. Okay, there is this formula to calculate the sensitivity lah. I'm not sure formula will be given or not sure. So for example for the midterm, I'm not sure lah. I think normally we given, okay, the formula, all the formula will be given, okay, for the midterm, for the final. So no need to memorize, okay. Normally we given the formula. So we avoid the student bring the notes, okay, on the final exam or on the midterm. That's why all the formula will be given, but you have to know how to use the formula lah, Normally the formula will be given. Okay, so next example, you can calculate the value of multiplier, all right, resistance on the 0 to 50 volt range of the DC voltmeter that use 500 microampere, microampere meter movement in the internal resistance of 1 kilo ohms. Okay, so first we have to calculate the sensitivity. Okay, 1 over full scale current. So the full scale current is 500 microampere. Okay, so we got S sensitivity is the 2 kilo ohm per volt. Okay, and then we have to use the formula lah. Okay, the formula to calculate the multiplier. Okay, RS equals to S multiplied by range minus by RM lah. Okay, so 2 kilo ohm per volt, okay, multiplied by, yeah, so you can see this one, so 2 kilo ohm per volt multiplied by 50, all right, volt. So that's why we can cancel out the V. That's why only left the ohms here, so minus with 1 kilo ohms. So that's why the answer is 99 kilo ohms lah. Okay, this is for RS, the RS multiplier. We call the multiplier resistor. Okay, RS. So actually this is formula. Normally we be given the formula. Okay, but you have to know lah. Okay, first you have to know how to calculate the sensitivity. Okay, sensitivity also we given the formula 1 over current full scale. Okay, this one we call a full scale, full scale current. Full scale current. For example, you give from this one, they said use of 500 microampere. Right, that is we call the full scale, full scale current. Okay, the range is the 50 lah. That's why we use the range from 0 to 50. We take the maximum lah. Okay, we take the maximum with 50, then minus with RM. Okay. Normally RM will be given. Normally RM will be given. Okay, so this is example. Example using the ensemble for use for voltmeter. Okay. Next is the multi-range voltmeter. Similar like before this for DC Ammeter. Okay, DC Ammeter they use the Ariton shine. Okay, Ariton shine. So this one we use the multi-range. Multi-range. Okay, the concept will be similar lah. Okay, so this one we have the R1, R2, and R3. For example, if we select the R1 here, okay, we have, and then we select the R2 and we select the R3. Similar like the ammeter, the DC ammeter. Okay, but this one we connect in the parallel. The resistor connect in parallel. Okay, you can see R1 parallel with R2, parallel with R3 lah. Okay, or we can convert into this one. Okay, convert into drawing like this lah. Okay, similar drawing. Okay, so you can see the figure 5.B ni is a simplified drawing lah from this one, from A to B. More clear lah, more clear. Okay. Alright, so this one the example. Okay, the example design the multi-range voltmeter range from 0 to 10 volts, 0 to 50 volts, 0 to 100 volts, and 0 to 250 volts using the ensemble movement with an internal resistance of 50 ohms and the full scale deflection of current the deflection of current of 2 milliampere. Okay, so this is an example. You can try this one. So for example, okay, we have 10, 50, 100, and 250 lah. So for example, we have here this one, maybe this one we call the 10, this one 20, okay, 50, 100, okay, 50, this one for 50, for example, this one for 10, 50, for example, so this one hundreds, and then this 250, okay, for example, right? Okay, the concept will be same lah. Use this one, The concept, the formula. First, you have to calculate the sensitivity, all right? And then after calculate the sensitivity, you have to calculate the multiplier resistor, Multiplier resistor. Okay, for example, if you want to connect to this one, so that means this one RS, okay, here. For example, for the 10, for the 10, that means RS here. Sorry, okay. For the first, we connect to this point. So RS equals to R1 plus R2 plus R3. Okay. Plus R2 plus R3 plus R4. Okay. So if we connect to this one, okay. For example, if we connect to 50, 50 volts here, so the RS will be R2 plus R3 plus R4. Okay, this one. If you connect to 100, okay, to V3 here, 100, that means, okay, this point to this point. So RS equals to R3 plus R4. Okay, if you connect to V4 here, 250, so RS equals to R4. Okay, that is the concept lah. First, if you connect to 10 point here, okay, 10 volt here, so that means RS equals to R1 plus R2 plus R3 plus R4. Okay, because the resistor in series we have to add lah. Okay, make sure so we have to remember this one, the basic of electrical. If resistor connect in series, we have to add all the resistor lah. So for example, you can see on the second point here, so this point to this point, so this one will be ignore. For example, for R1 will be ignore lah, because we will connect to this one. You can see the flow, the flow here.
Baik.
Okay, so will be flow here, right? Okay, that's why RS equals to R2 plus R3 plus R4. Okay, that's why if we connect to the 100 volts, that means only R3 plus R4. Okay, the R1 and R2 will be ignored. Okay, because not connected. And then similar like if we connect to 250, so only R4 will be calculated. That means RS equals to R4. Okay, that is the answer lah. Okay, next you can try this one. Try this one. Okay. So next for the voltmeter, we go for the for the DC meter is the ohmmeter lah. Okay, so the basic type of the series ohmmeter is shown in the figure 2.6. After that, I will show the figure. The ensemble is connected in series with resistance R1, battery, and unknown resistance Rx. Okay, the series ohmmeter is the simple and popular design, and is used to extensively for general service work lah. Okay, so the current flowing through the circuit depends on the magnitude of the unknown resistance. That means you can see the current flow through the circuit depend on the magnitude of the unknown resistance. Therefore, the meter deflection is directly proportional to the value of unknown resistance. Okay, this one. Okay, this is we call the ohmmeter. Okay, this is unknown. Okay, that means the unknown will be connected to the R1 in series. That's why if our total, we can calculate R1 plus Rx. Okay, and then parallel with this R2. Okay, that is we call the ohmmeter lah. Okay, ohmmeter. This is our resistor to measure the resistance. Okay, so actually the ohmmeter actually is to measure the resistor. That's why you can see this one is to measure the resistor, the amount of resistor. Okay, for example, for DC ammeter is to measure the current, DC voltmeter to measure the voltage, and ohmmeter to measure the resistor lah. Okay, that's why we put the unknown resistance here. Okay, so this is how to calibrate the series of the ohmmeter lah. Okay, this is how we calibrate the ohmmeter. Okay, so this one I think this one we have the video. Okay, actually this one we have the video so we I'll check the video first.
Jahil.
Okay, so this is from this is video for oscilloscope so I will check first which the video forgot to put where this video or for the explanation on the potentiometer. Okay, so this one in potentiometer, principle of potentiometer. All right, so this is okay. All right, so I forgot. Okay, so this one will be skipped first because I forgot to put where is the for video video to show the ohmmeter how to calibrate the ohmmeter Okay, so maybe you can try this one first. Okay, try this one try the example of this one Okay, first you have to calculate the sensitivity. Okay, calculate the sensitivity and then calculate the multiplier resistor Okay, first try to range from 0 to 10. And then next try to 0 to 50 and then 100 and 250 lah. Okay, so the RM equals to 50 and then the full deflection current of 2 milliampere lah. So using this formula using this formula, calculate first. You have to calculate the okay, sorry guys, sorry to share the slide. So try this one try this one first. Okay, next maybe next tomorrow after we do the tutorial, so maybe we can discuss about the ohmmeter ohmmeter. Okay, because this one we have the video how to calibrate the ohmmeter lah. Okay, this one quite tough to explain to all of you if you don't have the graphical so that's why I prepared the video presentation for how to calibrate the ohmmeter. Also actually we have a lot of video for how to calibrate the potentiometers and so on. Okay, so okay, so okay, so anyone get the answer for design multi-range voltmeter? Okay, for 10 volts, 10 volt. For 10 volts. So first calculate the sensitivity 1 over. I think the sensitivity will be same. Okay, the full current is here with the 2 milliampere 1/2 milliampere. Okay, this one S. Okay, S equal to 1/2 milliampere. Okay. So after that, you have to calculate the RS lah. RS S. Okay. The RS equals to S multiplied by RM range. Okay, minus by RM. Okay, so RM will be given. Okay, RM is the 50 ohms. Okay, range. Okay, range depends. For example, the first case is the 10. Okay, the first case is the 10 volts. Okay, next, for example, the next will be 50 volt. That's why we just use the same as, but change the range lah. For the first is the first 10 volt, second 50 volt, third is the 100, and last is the 250. Okay, that is to calculate the multiplier, the resistor here, multiplier resistor here. Okay. Okay, for example, okay, try number 1. 1/2 minus 3. That. Okay, multiplied by 10. Okay, the first. Okay, what is the first resistor? 4.95 kilo ohms, the first for the RS. And then use the same sensitivity, calculate the second. Second range is the 50. Okay, S multiplied by 50. Okay, and then minus with RM lah. RM is the 50 ohms. Okay, then next change the range to hundreds. Okay, the last is changed to 250. Okay, that is how to calculate the multi-range voltmeter. So okay, so this one maybe you can try. I think you can try this one. For example.
Macam sebab tu faham sikit. Ya. Aduh,
Okay, you can try another example. Okay, try another example.
Student. You are so student, you know. So student lah you, student.
Alright, class, try this one. Try example 3. Try example 3. This one. So you can see. Also, this is tutorial 2. Tutorial 2. You can see this one. The permanent magnet moving coil instrument. They have 3 resistor, electron shunt. Okay, connected across it to make an ammeter as in figure 2, and then the resistance for R1 is 0.05, R2 0.45, and R3 is 4.5 ohms lah. Okay, and then you have to calculate the range. Okay, the range for the ammeter. Okay, try this one using this on the slide lah. Okay. So the actually already given the tutorial already given in the group, in the WhatsApp group, so you can check lah the tutorial. So all the tutorial, okay, you can see this one. All the tutorial, we have the answer here. This one, I'll give the answer here, and then you have to double check lah, is it correct or not? Okay, maybe we do some mistake on the answer. So tomorrow we can discuss. So tomorrow we try to focus on the tutorial 1 first. Okay, next after we finish for chapter 2, we focus on the tutorial 2 lah. Okay. Okay, using this one, try using this formula. Okay, using this part lah. Try this one, Okay, so far any question for voltmeter or ammeter? So today we just focus on, we focus on the ammeter. Okay, so today we just focus ammeter and voltmeter lah. So tomorrow after we discuss on the tutorial one, so we go for the ohmmeter. So for today, recap for today is the DC ammeter lah. So DC ammeter is direct current ammeter, is to measure the current, to measure the current. Okay. So this is a concept of the ammeter, all right? So we use the unsolvable meter movement, okay? So this one only one range lah, only one range, okay? If we have more than one range, we call the Arrington shine, okay? So that is the basic how to use the DC ammeter, okay? DC ammeter that mentioned to you is to use the to measure the current. So maybe I recap this one for more understanding that I mentioned to you. All right. So if the current flow in the series will be same lah. So that's why you can see this one. So current will be flow here until this one will be divide by 2 lah. Divide by 2 Im and Is, and then here will be combined again lah. That's why here Im equal to Im plus Is. Okay, that's why I mentioned to you. So if current in series, okay, current flow in the series, so will be same lah. Okay. Example, this one we call it I1, and also this one also I1 lah. Okay, but the voltage will be different lah. The voltage will be different. Okay, the voltage here will be V equal to R1 I1. Okay, this one V. Okay, we call V2 equal to R2 I1 lah. Okay, that is the basic fundamental of electrical lah. Right, so that's why the voltage in series is different, but the voltage in parallel will be same lah. So for example, you can see this one. So this is one node, we call one node, and this is another node. Okay, that's mean here voltage here and voltage here is equals to this one lah. That's why you can see the equation Vm, okay, for voltage here equals to V voltage here. All right. So to calculate the Vm equals to Rm multiplied by Im. Okay. For Vsh, okay, here Is multiplied by Rs. Okay. So this is a fundamental for the unsolvable meter. Okay, make sure you have to remember this one lah. For example, like I mentioned to you, if current, okay, if you want to measure the current, make sure the connection in series lah. Okay, for example, if you put here for your multimeter that I mentioned to you, if you put here one point here to another point here, so it will be short circuit. It will be short circuit for the Rs and Rm lah. Okay, the concept of current flow to the lower resistor lah. Okay, for example, that I mentioned to you, if we put wire here. Okay, we put wire here, so automatically this one we call a short circuit lah. So current will be flow to lower. Okay, that means this one resistor is 0. Okay, R here will be 0 lah. Okay, that's why the current will be flow here. So if we have another circuit, another resistor here, so the rest will be ignore lah, will be short circuit. Okay, that's why the current will be flow here. Okay, if you put, for example, we put our digital multimeter here. So if the current is high here, the current is high, so maybe our multimeter will be lower. Okay, the fuse will be lower or broken. Our digital multimeter will be broken. Okay, because of the current directly through your digital multimeter. All right, that's why if you want to measure the current, you have to put, maybe if you, for example, you want to measure this this current, this Im here. Okay, this Im here. That's why you can put like this. Okay. That's why this one will be connected to this one. Okay, this is in series. Okay, you can see this one. That's why if you want to measure the Rs here, Is here, So you can put like this, our digital multimeter here, 1 point here, so another point here. So this one, okay, so that means current will be flow to this one, for example, our ammeter. So we flow like this. Okay. All right. So if you want to measure the voltage, okay, you can put the parallel lah. For example, we want to measure the voltage for here VM. So you can take your digital multimeter or voltmeter. Okay, using the voltmeter, put here 1 point. Okay, another 1 point here. So this one on the voltmeter, for example. Okay, for measure the voltage, we can tap on the parallel lah, on the parallel. Okay. Okay, for the parallel voltage will be same lah. For example, VM and VS is the same. For example, if another circuit here, so this is our supply and this is our circuit. Okay, so the current flow here we call the I1. So will be same with current here, I1. Okay, this one we call the R1, R2 lah, for example. Okay, but the voltage here will be different lah. So the voltage, okay, the voltage here will be V R1 I1. Okay, this one V for calculate the R2 I1. For example, to calculate the V2 here. Okay, that's why the voltage will be different. But if we put another one here, another one resistor here. Okay, for example, R3. Okay, so the V2 equals to V3 here. Okay, clear? So the voltage in parallel will be same. So you tap here, voltage here. So this voltage V2 equals to V3. Okay, but the current is not same lah. So the current here will be not same. Okay, the current, for example, is I2. I2 is not same with I3 lah, because the current will be, for example, I1. And then until this one will be, okay, will be split by 2 lah. Okay, split by 2. This one go for I3 and this one go for I2. But depends on the value of resistor. Depend on the value of resistor. So if the higher resistor, the higher number of resistors, so the lower the lower. Okay, that is the concept for electrical. Okay, guys, clear? Alright, so I will stop here first. Okay, so let's continue our topic for next week. For tomorrow. First, you have to try to the tutorial 1. So tomorrow we try focus on the tutorial first, tutorial 1. Then we continue on our topic lah, on our on the ohmmeter, ohmmeter for the chapter 2. Okay, guys. Okay, clear? Okay.
Clear, clear.
Okay, stop here first. Okay, see you tomorrow. Alright. So, assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam, Dokter.